So while these equations may be fun and interesting, they really don't bear a lot of relationship with what we do on a daily basis. You know, on a day-to-day operation, the measurements are going to be made in 3D. All these X and Y's and ground coordinates, all the measurements are going to be made in 3D, viewing stereoscopic photos. All the geometry and the math up to this point holds true, and it's the basis for everything. It's the foundation for every point that we're going to read. But how do we do it on an everyday basis? Well, there's one more concept that we need to understand without looking at any of the equations from here on out. You need to understand the idea of the coplanarity condition. And this is the understanding that for every single point on the ground, that light ray that forms the basis of the collinearity equations, that light ray leaves the object on the ground, travels through the film plane to the focal point of the camera. But since we have stereo photos and there is overlap and everything is imaged twice, once in this photo and once in this photo, and of course the line travels from the ground through the photo coordinate and the other photo to the focal point of the camera. There exists a three-dimensional plane that contains all of those points, both focal points, both photo coordinate positions, and the ground point. So the coplanarity condition just describes the fact that that plane exists, and that if we can make a measurement in each of the photos and start establishing the orientation of the photo and using multiple points and see where those photos are in space, that we can compute any ground point in X, Y, and Z, because now you see that plane is in three-dimensional space. We don't have to know how far it is, how far that is from the camera, because with the collinearity equation, you would know everything about the line except the distance from the camera to the ground. Here we're establishing that with the 3D space. So this is going to be the basis of what we're doing. So at this point, we need to kind of picture in space. All right, what we have here is a landfill, and we're looking at it in 3D. And you can see on the back side of the landfill there is there's a divided highway. On this side of the landfill there's a small road, and then this area in here is the landfill that we're going to be photographing. And then we have these three photos in space. Okay, exposure stations, the first, the second, and the third. That photography is exposed. We don't know anything about it other than when we look at it, we can see the landfill. If we look at it, two photos together, we can see it in 3D. The goal of the operation here is going to be to orient those photos in space in X, Y, and Z, omega, phi, and kappa, so that we know exactly how that film plane lies in space. Once we have that film plane locked down, we can pass light rays through the film down to ground points, make measurements in 3D, and use that coplanarity condition to relate the ground to the map. Let's take it one step at a time though. Let's say that the light, we're using light to measure and draw, using photos to make reliable measurements. Going back to the definitions, once that light is properly collected and stored, we need to reconstruct the geometry of the entire image space and the model space. It's a new idea here. The model space is when we have two photos together, we're looking at 3D, we have a three-dimensional model, a visual three-dimensional photographic model in 3D in model space, and then we need to relate that to object space, the real world. First thing that we're going to do is what is called an inner orientation. In this case, we are just going to be observing those internal control points, the fiducials. From there, we're going to begin building a framework of reference, a reference coordinate system for points to be measured. Because remember, all of our measurements are going to be in that photo XY system. That's the only real known that we have inside the camera. It is known based on the coordinate system, which is based on the fiducials, which comes from the camera calibration. So USGS tells us the coordinates for the known points, we measure them, we transform those into photo coordinates, find the photo center, and from there establish that that three-dimensional space. So imagine at this point we go back to our photography in space. We still don't know a whole lot about it with relationship to the ground, but we know that we now have constructed internally the photo space, the image space in that photo coordinate system. The next thing that we're going to have to do is relate one to the other. Now, there are distortions. If I say that, let's say I take the left photo and say that it is the reference. I'm going to call it square and true, and everything that I measure on the left is going to be held. If I take the right photo, based on its position, then there are certain distortions that can occur. One is called a base shift in X, and that's just going to move the points left and right. It's similar to elevation actually shows up in a base shift, and that's where the elevation measurements are going to be made. We'll look at that a little later, but just understand that if I lay one photo down and lay the other photo on top of it, if it doesn't line up perfectly, then one of the things I would need to do is slide it back and forth. Another thing that I would need to do is a base shift in Y. So imagine as the plane is flying along, it slides a little bit to the left as it progresses, and it's going to be up, a base shift towards the top of the photo. So if I lay the left photo down and want to lay the right photo on top of it and have it line up perfectly, then I'm going to have to shift it in X, shift it in Y. There may also be some rotation. This is called kappa, and as we rotate around the optical axis, you can see the distortions that are caused there at the top of the photo. The distortions are similar to an X shift at the bottom of the photo. Similarly, only opposite. In the left side of the photo, you have what looks like a Y shift, and then up and down based on what the rotation is. More or less magnitude depending on where it falls in the photo. So that's one of the distortions that has to be taken out. The next thing is a Z shift. If you think of a Z shift as the airplane, or the photo center moves up or down, you're moving closer or farther away from the object space, and in that case, you're actually changing the scale of the photography. So I might have to change the scale of photography, shift that in Z. That's what's indicated by that change in scale. V, we said, is rotation around the y-axis, and you can see how most of those show up as an X shift, but up at the upper corners and lower corners, there's a more of a Y shift involved, and they're inward or outward depending on which way the film is rotated. And then omega, a shift around the x-axis, and you can see the distortions that are caused there. Well, what we're going to do originally in the analog era, you would go through the practice of looking in the photography and making adjustments based on um, what you saw. So any distortions that you saw, and any time that you looked in the instrument and didn't see a perfect three-dimensional model, that one photo was distorted or shifted from where it should be, you would make these rotations. And the reason I listed those as X, Y, kappa, Z, phi, omega was that the operator would go through the act of rotating the images in three-dimensional space in that order, because as you progressed in that order, um, distortions that you took out were not affected by the next orientation. So if you started with the X shift and then it went to the Y shift and then the kappa at the proper positions, and there are what are called the six classical or six von Gruber positions that you'd clean up those distortions, and eventually you would end up with a 3D model that is, I look in the instrument, and very soon we'll actually start looking at some instruments. At some point we'll get out to man mapping and work on some instruments. But as I was looking there, I would see a clean three-dimensional model, and when I say a clean model, there would be no distortions involved in it. So once we have that three-dimensional model in space, I can make measurements in it. You can think of that as that little coordinate system to the upper left, but there's actually a real world coordinate system, an object space coordinate system. And the goal here is to take that little three-dimensional model, relate it to the object space, and then be able to make measurements in the model and output the coordinates in object coordinates. So that three-dimensional coordinate transformation is going to be the magic behind measuring in the model and outputting in ground. In order to do that, what we need is ground control points. So we have this three-dimensional model that I can view. Anywhere in there I can see 3D, and I can move around in it. If it's in color, it looks just like the real world. It's just a tiny representation of it. So what I need is ground control points, known northing, easting elevation points that I can make measurements in the three-dimensional model, relate those to the ground control points, and then tip and tilt the photos, the model itself, rather than just individual photos. Now I'm going to tip and tilt that whole model itself so that it properly relates to the ground. Once I have it related to the ground, I'm looking at the three-dimensional model in the instrument. There is a measuring mark in there. Okay, we talked about that floating dot, and it's that floating mark, that concept of the floating mark, where you put you put a mark in each photo, and as you move it around, it corresponds with something on the ground, and you're moving it in 3D. As it moves farther apart, then it would mean something higher. It moves um, closer together. It's something that's farther away. And as I move that dot around inside the three-dimensional photographic space, because I have that coordinate system locked down, anything that I measure in the photo space is now going to come out in ground units. So at that point, we just start making measurements, whether it's roads, buildings, um, hydrology, trees, just mass points that show the shape of the ground. All of those measurements are going to be done in 3D photo space, transformed to 3D ground space, and that's going to be the basis for the mapping that we do.